This is part 3 of Chemistry of Carbon and its Compounds. In this presentation, we'll be talking about acid chlorides and anhydrides, the process of acylation, and the chemistry of benzene. The assessment criteria for this podcast is the following. You are to be able to recognize acid chlorides and acid anhydrides. You are to be able to understand their reactions and the importance in organic synthesis. You should know and be able to use the mechanism of acylation and notice it in reactions. You should understand the role of acylation in the manufacture of aspirin. You should understand and be able to describe and draw the bonding in benzene. You should understand and be able to describe, using evidence, the additional stability of a benzene ring. You should understand and be able to explain why the structures of benzene cause it to undergo electrophilic reactions. And you should know and understand the general mechanism for electrophilic substitution in talking about the chemistry of benzene. Let's look first at acid chlorides. An acid chloride is a carboxylic acid derivative in which the OH portion of the carboxyl group has been replaced with a chlorine atom. Remember the halogens, remember their strong electronegativity. Acid chlorides react rapidly in water to return to the parent carboxylic acid. They are useful starting materials for the synthesis of such things as esters and amides. If you have to name them, you can name them by replacing the IC, for example in butyric acid, to YL. Therefore, butyric acid becomes butyl chloride. If it has an OIC ending, for example, pentanoic acid, and a chloride, it becomes an acid chloride, it becomes pentoyl chloride. So now let's look at this other group, acid anhydrides. An acid anhydride looks like two carboxylic acids stuck together. Anhydride means without water. Structurally, they are two carboxylic acid molecules bonded together after the removal of the water molecule from the two acid molecules. Let's look at the relationship of acid anhydrides and, of course, alkylation in organic synthesis. Acid anhydrides are susceptible to nucleophilic attack. Remember, nucleophilic attack is the creation of a carbocation. It's usually formed by polarity in the carbon bond. In this case, it's the carbon that's double bonded to oxygen. Acid anhydrides are also likely to participate in addition reactions. And we'll see in this podcast that these reactions are important in the area of the making of drugs called pharmaceuticals, and also in benzene reactions. Paracetamol, a common analgesic drug available in Kazakhstan, is used with ethanoic anhydride reacting with an amine group, remember a nitrogen group, to make aminophenol. And acid anhydrides work very well with benzene to create side chains off of the benzene ring to create pharmaceuticals and many other items. I talked about acylation in the previous slide. Let's talk and see what an acylation is. Both acid anhydrides and acyl chlorides are acylating agents. Take a look at the acyl chloride below, RCOCl, acyl chloride. If it reacts with an acid, HY, you see the chloride removed and the other half of the acid, it becomes a part of that RCO group. The Y halogen attacks the carbocation, causing the carbon double bond to be broken, and in this case, HCl produced. Acid anhydrides also undergo acylation. You just saw above an acyl chloride. And in those reactions, you have nucleophilic substitution followed by elimination reactions. Acid anhydrides work with water to produce carboxylic acids. Acid anhydrides work with alcohols to produce esters. Acid anhydrides work with ammonia to produce amides, and acid hydrides work with amines to produce substituted amides. Let's take a look at acylation in the manufacture of aspirin. Okay, let's see if we can see the nucleophilic reaction and then the elimination reaction. The first thing we see is the carbocation being created. Notice the attack of the electron-rich oxygen on the electron-poor carbon and the subsequent bond breaking. The following video describes how aspirin can be made in the laboratory. Pay particular attention to the steps that are used in the laboratory. Remember, these steps are not what is done in the commercial manufacturing process.
Okay, first we need to add 3 grams of salicylic acid. Weigh that out. On 2.9. 3 grams on the scales. And we're going to put that into an Erlenmeyer or conical flask. And to that you need to add 6 ml of acetic anhydride. So the acetic anhydride has gone into the salicylic acid, and then finally we're going to add about 6 drops of phosphoric acid. So they're all the ingredients for making aspirin. We're going to swirl them together and then add it to a beaker of warm water for about 15 minutes. Okay, now that's been in the warm water for 15 minutes and it's all dissolved. We're going to add 20 drops of cold water. And that will reduce our temperature a little bit. And then we're going to add 20 centimetre cubed of cold water. So we didn't want to add the water all in one go because we want to bring the temperature down slowly. And that will now go into the fridge. Once the mixture has been in the fridge and crystallisation has occurred and you get a white solid, we're going to put it into Buchner filter and wash it through with some ice cold water. The Buchner filter works by causing a suction, so the water is going straight from the tap down into the sink, and that is pulling air through that other tube out of the Erlenmeyer flask, forming a vacuum there and pulling the product down with it. The cold water through the Buchner filter cleaned off any impurities. Now we're going to perform recrystallization on our aspirin. So we're going to take the crystals out of the Buchner filter and into a flask. We will add 10 ml of ethanol. This will be stirred in some warm water to heat it up to dissolve the crystals. Now the aspirin crystals have dissolved in the ethanol, we are going to add water, 25 ml of warm water. And this will be covered and the crystals will start forming again as the solution cools. So to speed this up, we will put it in the fridge. Now the aspirin has recrystallised, you can see that it has made very, very small crystals now, and they really look rather pretty. Now we need to put them through a Buchner filter again. In goes the filter paper into the Buchner filter. This is starting the drying process, sucking out all the moisture from the crystals.
Well, we've looked at aspirin and acid anhydrides and acyl chlorides. Now let's look at benzene. Benzene is a highly unsaturated molecule, C6H6. There's a 1-to-1 ratio of carbon to hydrogen. It shows little tendency immediately to undergo addition reactions. A man by the name of Kekulé in 1865 suggested the structure of a 6-member carbon ring with alternating single and double bonds. This symmetry seems to explain many, but not all, of the properties of benzene. For example, all the carbon-carbon bonds are of equal length, and the enthalpy change for hydrogenation of benzene is a negative 208 kilojoules per mole, making it a very stable molecule. Let's take a look a little bit closer at the idea of this benzene ring and this alternating single and double bonds. In a benzene ring, 6 carbon atoms are sp2 hybridized, forming 3 sigma bonds. The angles are 120 degrees. You can see the beginning of a benzene ring with 3 sigma bonds. 1 unhybridized p electron on each carbon remains. The electron density of the p orbital, you notice on the right in that picture of the 6 p orbitals, its dumbbell shape, is above and below. We believe, instead of pairing up to form alternating pi bonds that shows in the picture on the left with double bonds, that what really happens is that the p orbitals spread out and make an electron cloud. The next assessment criteria is to understand and be able to describe, using thermochemical evidence, the additional stability confirmed by the ring structure. Well, let's look at some thermochemical evidence. Let's look at cyclic compounds that have 6 carbon atoms. Well, cyclohexene is one. Its enthalpy of reaction is 120 kilojoules a mole. 1,3, cyclohexadiene is 232 kilojoules a mole. 1,3,5 cyclohexatriene is 316, and benzene is a minus 208 kilojoules per mole. So you can see that something must be going on with those pi bonds in order to create such a low enthalpy of reaction. Understand and be able to explain why the structure of benzene causes it to undergo electrophilic substitution. Well, we talked about nucleophilic substitution, and when we talked about acyl chlorides, now we're going to talk about electrophilic substitutions in benzene. Benzene is subject to attack by electrophiles. Once attacked, an electron pair is attracted to the electrophile. The pi electrons that are above and below the benzene ring are disrupted. You can see the effect of the electrophile on those pi electrons in the diagram below. A carbocation intermediate form has both the entering atom, the E, and the exiting atom, H, a hydrogen, attached to the benzene ring for a very short time. The hydrogen ion leaves and the substitute remains, and allows the pi bonds to reassert themselves and become again the benzene ring. Let's look at these following questions to start your thinking. I would ask that as you read these questions, look back on the podcasts and find information to help you answer these questions. Answers to these questions can also be found in those things we do in the classroom.